Hello everybody, welcome to the next lesson in the motion unit. So we're going to look at a video physics example. I'll show you what that means. It means you just watch a video and you can take measurements from it and learn about the physics of the world around you. And then we're going to look at just a little extra help with the thrown downward kind of gravity questions, and then tackle the harder type, which is when an object is thrown upwards, analyze all the motion and so on. So the video here, I'm just going to pause quick so I can grab that video. All right, here we go. This person, Dana Kunze, or Koons, I'm not sure how you pronounce his name, attempting to tie the world record high dive. Which begs the question, why not just jump the extra foot? I don't know if there's regulations or what. I don't know how it works. I'm not in the high diving world, but check out how high this thing is. All right.
Comer to this event. He's been world target diving champion, world high diving champion, has more records than anyone else in the sport of high diving.
Watch this. There's people there's the platform or the tower, whatever you call it, ladder they climbed up, right?
Dana, this is Ken Sitzberger and Diana Nye at poolside. Can you hear us? Yeah. How do you like your position, buddy? Well, I felt real strong on my first dive. And
he is way up there. Like if this was a new video, you'd swear it was AI or modified or something. But I've been using the same video for the last like a long while. Let's just say I don't want to feel too old. 20 years. Yeah. Anyways, so he dives, and so he's talking to the guy by a little radio headset, I guess, of some sort,
the scores are big,
which they had back in the 70s, I guess.
I can get a good dive in there and up that scores a little bit. I need a win real bad.
So crazy. They have the spray on the water to help them enter the water, but also so you can see the water, right? Anyway, so let's jump ahead to
Ankles taped.
Oh, really? Is it not going to let me do it?
Ankles taped.
Oh boy. All right, let me just pause for a second. All right, I can't really get it to let me just to move wherever I want, so I have it paused where I need it. So I want you to be ready with a stopwatch, and for when he goes off of the tower, basically just kind of falls off of it. Doesn't really jump up much, basically. Time, how long it takes to go to the water. Okay.
He's trying not to be too exuberant, but I know from my experience with Dana over the last 3 or 4 or 5, 6 years that he loves his position. He's the second to last diver. If he does a good dive, there's a good chance the last diver will scratch. He's Pat Picard's a rookie, and if Dana nails one, which he's very, very capable of doing, the competition will be over.
And don't forget that these divers are not only athletic competitors, they're performers. They go all over the world, the Oktoberfest in Germany, etc., performing for the crowds. And they know how to salute, and they know how to give a smile even when they're hurting, when they hit bottom.
His dive is far more difficult than any dive that the other competitors have used. It's a reverse triple somersault.
He's going to do a reverse triple somersault from that height, and he's going to live, hopefully.
Baccia did a single somersault, and most of the other competitors did double somersaults. He's doing a reverse triple somersault back towards the platform.
Right, so
you can see him going through some of his arm
starting
movements.
at 2.8.
Jump. He's in good shape. He knows where it is.
And boom. So 2.8 to 2.12. If you timed it or so.
All right! He drilled it.
So around 4 seconds or so. You can tell the era of the timing of this video back in the 70s sometime. Anyways, so what can we calculate from this video? And the answer is basically everything, because we understand physics, right? So we are given the initial velocity. We know the displacement, the minus 72, the 172 feet that he fell. Convert that to meters, it's 52.43 meters. Who cares? We'll just use it. And we know the acceleration down due to gravity, right? So we can calculate the final velocity, and yeah, pretty much it, right? We measure the time. So one thing we can do actually is we could calculate the final velocity. We can calculate what the time should be. There's all sorts of things we can do. Okay, so if you timed it, you have an idea what the video showed for the timing, we'll calculate what the time should be, and so on. So I think this is one of those ones where we want to calculate the final velocity first, otherwise we end up having to solve a quadratic. So that's why I'm going about it this way. So let's do this. Oh yeah, this one. So let's do this here. If we are looking at using V1, so V1 delta D and acceleration, and we're going to figure out V2. That allows us to use, or gets us to use this equation here. So V2 squared equals V1 squared plus twice acceleration delta D. And just notice if we had have wanted to solve for time first. So let's get rid of this one and say, okay, if we were looking for time, you could tell it would be this one here. And so you'd have a quadratic, right? So delta T first would involve a quadratic. That's why that's why I asked this question first, basically. So here we go. We got our final velocity we want to know, and we have our initial velocity of 0 squared. Who cares, right? It's, anyways, we got minus 9.8 and our minus 172. So because they're both negatives, it kind of cancels out and so on. But we got our V2 squared equals whatever that is. So we need our 2 times 9.8. 2 times 9.8 times the 172. No negative buttons needed here. Gives us, oh, it wasn't supposed to be 172. Sorry, it's supposed to be the meters, eh? Because if you notice, this is in meters per second squared. And so we need this to be in meters as well, right? We need this to be in meters. So they communicate with each other or jive with each other properly. So we need the 52.43. I noticed that early rather than getting a bunch of numbers and then the next page calculating time would have been completely wrong, of course. So 2 times the 9.8 times the 52.43. I'm not worried about how to do the conversion at this point. Obviously, you could just use Google, or you could find out what the conversion factor is and get it. But basically, look at it as you're given the 52.43 number. So 1027.628. That's the square of the final velocity. So we can square root both sides. Technically, mathematically, we get a plus or minus. But of course, we're going to use the negative number because it means down, right? So we're just going to take the square root of that thing. And we get 32.1 or so, probably about the level of accuracy you might sort of trust, right? Meters per second. And so, in other words, if I wrote it as negative, that up, therefore the final velocity, right? Final velocity is, therefore the final velocity is the 32.1 meters per second down. So that just allows us to get the final velocity. Then if I had, let's go. I think I'm ahead of myself here. I'm just going for it though. If we look at the time, then we have acceleration equals delta V over delta T. And so we would have the negative 9.8. We'd have the delta V. We'd end up with that number we had there from the final velocity of the 32.1. So the minus 32.1 velocity downward and the acceleration downward, signs matching. And so we solve out for time, right? We can just multiply both sides by delta T, get rid of that, and then divide both sides by the negative 9.8. And we end up with delta T equals the 32.1 divided by 9.8. 32.1, or the full number there, if we want to keep it, it's fine. Divide by 9.8 gives us the 3.7, or 3.27. I think I remember approximating around 4 from the video, but obviously just based on the timestamps in the video, which would be give or take half a second. So you probably got a number similar to that, right? Therefore, you know, we could say it should take, right? So it should take 3.27 seconds to for him to fall and hit the water and so on, right? And so we have the opportunity to actually talk about whether or not air resistance is a factor here. So if we were looking at doing the work here, yeah, this is numbers I got from a class when we did the video together. So we got an average of about 3.27 seconds. It worked out amazing. Literally, that was just numbers that were said by the class. So I have this page, whatever, saved because it just turned out so amazing to be exact like that. I didn't realize actually because I didn't have the number in advance calculated. If we did the VT graph method, obviously we could know the displacement and oh yeah, this is the one where you have the two equations, two unknowns business, right? And so instead, first you could get the time and so on, and there's the conversion factor and so on. So we've already done the work for this, but I mean, the equation work is what we'd expect, right? The other one, I'm trying to losing track of what I did in this old slide version of things, but we calculated out what the acceleration was and so on. Oh yeah. So the number in the end is multiplied by 3.6 to give that 115 kilometers per hour, right? That conversion from meters per second to kilometers per hour. So what I look at this as an opportunity for us to say, okay, well, wait, the time is supposed to be around 3.27 seconds to fall, and obviously there's air where this person is jumping. So I think what we're noticing from this is that air resistance isn't a very big factor for a human falling. Okay, so the actual numbers from the video, it's not necessarily going to work out that exact every time, but clearly air resistance is not a huge factor. It's a big factor for a piece of paper falling, but not for a human, not until you reach really, really fast speeds. And we'll talk about terminal velocity later on, once air resistance becomes a factor. This one's just left with solutions for you if you want to try it. Okay, so solutions on the next page. And then the thrown down case, we'll just go through an example of that. So if you're picking out the information you're given a velocity down, straight down, of initial velocity. 6.9 seconds later it lands, and we know the acceleration. Okay, so you're given information, and the unknown would be like how far down is it, and the final velocity, the two things you could figure out. Okay, so if you did the selection process for this question, obviously you had the option here of pausing and trying, right? If you did that, or if you're doing that or whatever, and you press play to get some help, this might help you here. And then you can circle what we have and what we're looking for and so on, right? So the V1s, we have, I'll mark on each one of those, the times. That was right now, that's why it's not as pretty. And the acceleration. And if we're finding the displacement, then you pick the one where you have 4, which would be this one right here. So to get displacements, no problem. We just plug numbers in and calculate it out. Okay? That just gives you how far down the thing lands and so on. And obviously we could go and calculate the final velocity too and so on. Okay, that's all old news. On to the new news here, all right? So this is the main focus for today, other than I think it's neat to be able to get a video that wasn't intended to be a physics lesson, right? And take real physics measurements from it. So refer to it as video physics. If you Google video physics, you'll see a bunch of videos that end up analyzed that way. So here we have now, in this thrown upward example, we have a rock. The mass is given, which is a red herring, they call it, or whatever. Basically, you don't need the mass, obviously, as long as air resistance isn't a factor. I was thinking of a different slide here. So it's tossed upwards with a velocity of 11 meters per second from just beside the edge of a tall building, and so it manages to fall all the way to the ground. Okay, so essentially it's thrown upwards and then falls down to the ground, but having started at a height of 15 meters. So you're asked to draw a VT graph to represent the object's motion from when it was tossed all the way to when it lands on the ground. Label the VT graph with spots that correspond to maximum height back at the top of the building and hitting the ground. Determine the maximum height the ball reaches above the ground. So that'd be height that it gets above the building. Add them up, right? What's the velocity and acceleration of the ball when it's at the maximum height? Determine the ball when the ball is back to the initial height and the velocity it has. Determine how long it takes to land, and these are the full package of questions here, right? How long it takes to land and the final velocity it hits the ground with. So hopefully you're looking at this and thinking, okay, well, we can look at given information and just calculate things as we go, right? So this is a similar question to the sort of similar, at least anyways, to the challenge question from lesson 33, because we have a direction change, right? So that's what makes this a little harder. So pause and try if you want. We'll label a VT graph, and it should look like this, right? So we should start with a velocity upwards of 11, and that velocity is going to change as we go and so on, right? And so this should be the spot you would label as when it gets to the maximum height, because that's when it has zero velocity, so it comes to a stop at the top, briefly, of course. Back to the initial height should recognize sort of some symmetry here. This represents how far it went up, and then, of course, the same amount for the way back down, right? So this is in there, delta D up, and then, of course, that would equal the delta D back down, right? Delta D up and down, or back down, or whatever. Yeah, so those have to be the same size, which, and the idea that we end up with that same velocity down as we had up, we'll look at that soon. But this is basically, what went up came back down. So the faster you toss something up, the faster it comes back down, the faster the velocity it has when it comes back down. But we'll see all the proof of all that stuff. And then finally down here, it's going to get to the ground at some point way later on. Okay. All right. So next question, determine the maximum height the ball reaches above the ground. Press pause and try if you'd like to be an active learner. And this is what it should look like when you compare to your efforts here. So hopefully you're noticing that you were given an initial velocity of 11, acceleration, and in this case, the final velocity. Okay, so what we're trying to focus here is that there's some hidden information. It didn't say in the question, determine the maximum height it has when it reaches a velocity of 0. Like the velocity of 0 is implied. So we can obviously just go ahead and calculate acceleration equals delta v over delta t and get a 1.12 seconds. Okay, that 1.12 seconds can just go into the area formula if we're just doing good old VT graph method. No reason why not, right? 1/2 of the base times the height equals the delta d, and so we can put the time in for the 1.12 seconds and calculate out that it's 6.16 meters above the building, right? So we could add it up if you wanted, say 21.16 off the ground, but I mean, just depends what you're looking for, right? That should be good. I think there's nothing new there. The only thing that's new is we're dealing with part of the question, right? But it's the same as the original kind of questions we've done. It's just there's more to this story. We didn't just go to the top and that's it. So the question is, what's the velocity? Oh yeah, what's the velocity and the acceleration of the ball when it's at the maximum height? So you should just think about what your answers are for this, okay? So when it gets to the maximum height, obviously the path of the ball, looks like it's going up and then it's coming back down, right? Roughly, not moving sideways much. Up here, what's the velocity and the acceleration? Well, the velocity is 0. The acceleration, though, is not 0, right? So it is not 0. It is still that negative 9.8, or else it would just stay at the top, stay floating there. So that's a reminder question there of something that's misleading and hard to get your brain to accept it and spit out the right answers without some careful thought. Next question, determine when the ball is back to the initial height and the velocity it has. So when does it get back to the initial height and what velocity does it have? Pause and try if you'd like. The first way I'm going to go through this with logic here is just to say, well, it has the same acceleration on the way up as down, and it's going to take the same amount of time to change by 11 meters per second in both cases, whether you're going from 11 to 0 or from 0 to minus 11. So very logically, it's going to be another 1.12 seconds, and our final velocity is going to be minus 11, right? The what goes up must come down kind of logic of things. It's just something that's true, okay? We can look at it another way, though. So again, another way you could look at this is logic number 2 is, we know it gets back. We know for sure, guaranteed, there's no assumptions. It gets back to the initial height. That was part of the question. So we're back to the initial height. And so what that does, it gives us something to calculate. We know the initial velocity is 11. We know the acceleration is the negative 9.8. And there's, if the delta D is 0, by definition, we're back to the initial height. Okay, so we're not making any what goes up must come down and the speed change, whatever. This is involving a little more intuitive logic. Whereas this is just straightforward, we're being told we're back at the initial height. So if you pick the equations from the sheet, you end up using this one, that goes to 0, put the 11 squared and rooted and so on. Basically, it algebraically, without even putting numbers in, shows us that the final velocity is equal to plus or minus the initial velocity. Obviously, it's going to be the negative in this case because it's on its way down, right? So the logic used in number 1, that it would have to be the same amount of time for that velocity change, and in fact, you end up with that same velocity in the downward direction, right? That's fully verified by this version of working on it. Okay. Later on, I think maybe we'll talk about it, but I mean, we could mention it here right now that people sometimes have problems with this idea, and especially in the context of a bullet fired straight up. Okay, so a bullet fired straight up goes up, comes back down. It's deadly on the way up for sure. It's just fired from a gun. What about on the way down? Well, this calculation is showing that the bullet would come back down with the same velocity it was launched with, give or take a little bit because of air resistance, right? So take a little bit, I suppose. Could be a little less because of air resistance. But if you look at Dana Kunze up here, air resistance we found was not much of a factor, right? At all. It was basically exactly the numbers we thought. So, I'm not sure I'd trust my life with the air resistance of a bullet trying to slow it down. And in fact, there are documented cases of people dying from a bullet that's on its way back down. Okay. So, and people charged with murder because they shot a bullet up in the air, they came back down and killed someone. They're charged with involuntary manslaughter, or I forget the terminology of it, but they're charged with manslaughter, essentially a form of murder. You have to be responsible for your actions, right? Even though they didn't intend to kill someone. So the next step here, determine the velocity the ball hits the ground with. So the velocity the ball hits the ground with, I don't have this one set up here. I have it. Maybe I just have an extra page here. No, velocity the ball hits the ground with. Different number here. Okay, so anyways, it's really this diagram here that we need, right? Where we have to think of this sort of maybe you could decide anyways to think of this as a new question, right? Where we have an initial velocity of negative 11 and so on. Right now I'm answering how long it takes to get to land. But let's just go back and do the other way as well. So if you picked based on the equations, you'd have your acceleration, your displacement. Notice that our displacement is negative 15. Okay, so we end up with a negative 15 displacement. Just think for a second here. Yeah, it works either way. Because if we're starting at the building, back of the building, either way you have to go down to the bottom. But you'll see that you can take this thing as the initial velocity could have been the 11 even in this case. But I'll elaborate on that in a bit. But anyways, if we did treat this as a new question, we'd have our minus 11 starting velocity, our acceleration, and we drop 15, right? And so it seems very straightforward, and you're just like, okay, you calculate it out, you get that the final velocity is going to be plus or minus 20.37, so obviously the down direction, right? So just note, That's, in some cases, it's nice to think of this as a new question, but it's also nice to realize that you didn't need to for sure. So if we thought of the whole situation, like v1 equals plus 11, so the thrown upwards velocity, the displacement of negative 15 now still makes sense, because the negative 15 means you end up down from where you started, right? So it doesn't matter whether you started on your way up or on your way down, you start at the top of the building. Okay, so that minus 15, the overall displacement back to that vector knowledge we talked about. The fact that it went up and then back down a bit doesn't matter. Okay, and there's another slide that's dedicated to that, but I'm just ahead of myself here. So the acceleration is the negative 9.8 still, and so on. So notice that we would have had a plus in here instead. Does that change anything for this question? Absolutely not. Okay, so I suppose in my previous slide I could, I could say that you can think of it as a new question, but you don't have to. Okay. And then how long it takes to land. Velocity hits the ball with. We have the. Yeah, I messed up in terms of which question is being asked here, right? So we did end up calculating the velocity hits the ground with as I was supposed to, I guess. Just had things mislabeled. If we look at how long it takes to land, pausing and trying. But yeah, we end up with, think of this. We have the initial velocity of the minus 11. If we want to think of it as this as a starting point, we have the 11 down, we have the final velocity of 20.31 down, and the acceleration, we can calculate the time it takes to land, but that's from like when it got back to the initial height. So you would just add them all up. Right? That's one way of doing this. You just add them all up. So this one here, not finding the stuff I was supposed to have, but it was 1 point something, wasn't it, before? 1.1 seconds, I think. All right, so many slides. Oh my gosh. Original. Okay, so somewhere in here we'll have that time. 1.12. So 1.12 seconds, and you would just add it all up, right? So if we have 0.95, you'd have the total time, right, to land would be the 1.12 to go up, plus the 1.12 to come back to the building, and then plus the 0.95, right, for a grand total, and just add it all up. And I guess I may as well, because I'm going to compare to what you get if you just do it from the very beginning. 1.12 plus 1.12 plus the 0.95. And so we get 3.19 seconds. On a slide here somewhere, but there it is. So, or we could look at the whole situation, in which case we're looking at, it was launched upwards at 11 and had the acceleration down and the overall displacement down. If we were solving for the time, notice that the equation we pick would be a quadratic, and so you have to solve. So instead we could get the velocity first, right? So choosing the positive velocity and the displacement still makes perfect sense, okay? In this case, the minus 15 maybe felt more logical, because it's like, we're going from the building directly to the ground. But whether you're going from the building directly to the ground, or the building and then just eventually ending up at the ground, having gone up and down, doesn't matter, right? Same as the IndyCar race car having a displacement of 0 overall. And then, yeah, so basically what I was trying to get across there was, you'd have to ditch out and solve for velocity first. Then you could go back and get the time, right? Once you have that time, you can just, or the other velocity, I should say, you can just solve for time. Okay, so that number there should end up being that grand total number that we had. So we can do this, the minus 9.8. We're gonna have the negative 20.37. So I'm just gonna do 20.37. Sure I have the right thing here. Get this out of the way. 20.37 and the 11 combined for a total of negative 31.37. And obviously, I'm just going to do the usual, multiply both sides by time, divide both sides by negative 9.8. I don't always just do this in one step on the board, but I think we've done it enough times super thoroughly that we can get away with this. And so really, we're just doing the 31.37 divided by 9.8. So divide by 9.8 gives us that 3.2 number, right? So that 3.2 number that we added up all of the individual times up here somewhere down here, right? So there's that, within rounding errors, of course, right? I just kept a different number of decimals in two different spots. Yeah, so the idea of the hidden variables and keeping track of what you know. So when you're asked, what velocity acceleration when it's at the maximum height, so final velocity 0. When it's back to the initial height, the displacement 0. When the velocity hits the ground with, the displacement is negative 15. Like there's kind of understood information that you have to recognize. Should be understood kind of information, I should say, right? So you have two questions like this. You have one that's thrown up with 18 and so on. This one's, thrown up with 11 and so on. I don't think that's the same numbers. Oh, 11.615 meters. 11.615 meters. Yeah, I'll update the question page when I save the file. I gave you the same ones we did in class. So I'll fix that. So you have some to practice, okay? But you've got that one for sure, at least anyways, if you're just going to get started on that right now. And yeah, that's all for now. So thanks for watching.